materials, and safety devices. So the fourth is, what is a steam turbine? A machine that turns heat steam into motion. How it works: hot, high-pressure steam pushes on a fan-like blades like a pinwheel. The, the spinning shaft then powers a generators to make electricity. Number 1. Rotor. The spinner, the long shaft with all the blades attached. This is the part that turns. Number 2. Blades, the pushers. Small airfoils attached to the rotor then catch the steam and make it spin. Number 3. Casing. The shield. The strong fixed outer housing that holds the steam in and directs it toward the blades. Number 4. Bearings. Special supports that keep the rotor perfectly centered while it spins. Number 5. Seals and gasket. Material used to prevent high-pressure steam from leaking out. Material used in manufacturing. Turbines work under extreme stress, very high heat and high pressure. Rotor casing material. Usually chromium molybdenum, steel chrome moly. Blade material. Often stainless steel or nickel alloys for high pressure stages. This material. Babbitt metal, a soft alloy made of tin or lead for low friction and protection. Seal and gaskets. Material. Graphite carbon rings or soft metals for tight sealing under heat.
A small steam turbine in a refinery, but a big effect on revenues. When it is not running, the operators lose several $million a day. Therefore, an all-new steam turbine has to replace the old one, perfectly matching all its parameters. Building it onto a steel frame saves 2 weeks of plant downtime because the old foundation doesn't have to be demolished and recast. After the initial planning, work can start on the shop floor. Here, the major components after their machining on multiple high-precision machines. The assembly onto the steel frame has already started, with special attention being paid to the sealing surfaces. The documentation and control of all gaps and clearances during assembly provides a perfect result. At the same time, work is starting in preparation for the final assembly, as the lower housing shell is mounted onto the steel frame and the pipes are welded into place. The joining of the individual parts is, like the machining, precision work and requires a high degree of experience. Finally, the last parts can be assembled and the newly built turbine is ready for the final tests under steam and load. We are only satisfied when our customers are, and they are. Trust the power people. Siemens Energy.
Safety devices keeping the system safe. Number 1. Overspeed trip, the emergency brake. A device that immediately shuts off all steam if the rotor spins too fast. The most important safety feature is the overspeed trip. If the main control fails and the turbine spins too fast, it could fly apart, causing a catastrophe. The trip stops it instantly. The low vacuum trip shuts down the turbine if the pressure in the condenser drops too low. A low vacuum trip prevents problems from backing up. If the condenser isn't working right, it can cause problems in the main turbine. Number 3, emergency stop valves. Very large, fast-closing valves that can instantly block all steam from entering the turbine. These emergency stop valves are the final physical barrier. They can be closed manually or automatically by a trip. Operational control mechanisms. Number 1. The governor, the speed controller. A system that automatically adjusts steam flow to keep the turbine at a constant speed, usually 3000 or 3600 RPM. The governor is the brain of the operation. It constantly watches the speed. If the electricity demand goes up, it opens the steam valves a little more to keep the speed steady. Number 2. Control valves, smaller precise valves that the governor opens and closes to manage the exact amount of steam entering the turbine. These control valves do the fine turning. They are told what to do by the governor. Number 3. Monitoring system. Sensors that watch temperature, vibration, and bearing oil pressure. Alarm go off if anything is outside the normal limit. Operator constantly monitor these systems. Early warnings or alarms let us fix small problems before they become big, expensive ones. Summary key takeaways for you guys. A turbine steam energy into rotation. Remember the core functions. It is a big complex engine that turns steam into motion. Strong materials like chrome, moly are needed for high heat pressure. The material must be extremely strong to handle the intense conditions. The governor controls speed during normal operation. The governor manages the speed by controlling the steam flow. And the last one is the overspeed trip. Is the ultimate emergency shut-off. And never forget, the overspeed trip is the most vital safety feature in the steam turbine.
Several of the auxiliaries associated with turbines. Now we're going to take a look at a few additional auxiliary systems that are vital for safe and efficient turbine operation. Some of these auxiliaries protect the turbine and some control its speed. The speed of a turbine must be controlled within the limits that the turbine is designed to handle. If the speed increases beyond the maximum limit and is not controlled, the turbine could literally fly apart. On the other hand, if the speed is too low, the turbine won't provide enough energy to drive the equipment. It's also important that the speed be maintained at a constant level during normal operations. Fluctuations in the speed are inefficient. Hunting is the term used to describe the action when a turbine's control system fluctuates while searching or hunting for the proper speed. In addition, the turbine must be protected from operating under abnormal or unsafe conditions that could seriously damage the turbine, the driven equipment, and related systems in the facility. Various turbine protection devices help prevent this kind of damage from occurring. A governor is the device used to control the steam flow into the turbine and maintain the speed at the desired value without hunting. This is an example of a mechanical hydraulic governor. It has a hydraulic system that reacts to changes in the speed of the turbine shaft. If shaft speed increases or decreases, the governor, through a linkage, adjusts the position of the governor valve in the steam chest so that a constant turbine speed is maintained. As you may recall, the position of the governor valve determines the amount of steam being supplied to the nozzles. And in this way, the amount of steam supplied determines how fast the turbine operates. In addition to auxiliaries for regulating speed, there are also various devices used to protect the turbine during operation. The first of these protective devices that we'll talk about is an overspeed trip mechanism. The overspeed trip mechanism is used to protect the turbine from being damaged in case the turbine speeds out of control of the governor. As you may imagine, a turbine that flies apart due to uncontrolled speed can be very costly to a facility. It also endangers the health and safety of the turbine operators. So it's vital that you have some way to quickly stop or trip a turbine if overspeed conditions develop. Generally, if speed goes beyond a certain limit, a trip valve in the overspeed trip mechanism automatically closes to stop the turbine. There are a variety of arrangements for overspeed trip mechanisms, but they all operate on pretty much the same principle. Basically, if the turbine overspeeds, the shaft's centrifugal force will cause the trip valve in the overspeed trip mechanism to slam shut. When this valve shuts, it cuts off steam to the steam chest and stops the turbine. Also associated with the overspeed trip mechanism is a hand trip lever that the operator can use to trip the turbine by hand. Manually releasing the lever's latch causes the trip valve in the overspeed trip mechanism to shut and stops the turbine. Whenever the trip has been activated, either automatically or by hand, it must be reset manually before the turbine is put back into operation. Some turbines have additional protective devices that will automatically shut the turbine down if an unsafe operating condition develops. These protective devices are commonly triggered by conditions like low lube oil pressure, high bearing temperatures, or some other abnormal condition associated with operation of the turbine, the equipment driven by the turbine, or the system in which the turbine is used. Typically, such devices involve a solenoid trip that is operated by electrical inputs from the system that has developed the abnormal condition. In this example, a turbine drives a pump. If the pump's oil level drops below a certain point, a solenoid trip is activated to stop the turbine. This prevents the pump from being severely damaged by continuing to operate without proper lubrication. By now, you should have a good general understanding of the basic components and functions of a typical non-condensing steam turbine and its auxiliary systems. This would be a good time to look over the turbine you'll be operating in your facility and become familiar with its specific components. After you've done that, you'll be better prepared to look at some actual operation procedures. Also, before going any farther, take some...
We see first the thrust collar, which bears against the thrust pads during operation. Just ahead of this, there is the portion of the shaft which sits in the journal bearing. This area should be perfectly smooth with no indentations or marks. Moving further along, we come to the gland seals, which are needed to reduce steam leakage along the shaft. We'll be talking about this arrangement in more detail later. We now come to the series of wheels, or discs as they are known, which extend along the length of the shaft. Blades are fitted all around the periphery of the discs and are held firmly in place at the roots. On many machines, further support is provided by fitting rings or shrouds around the outside of the blading. Note the much larger size of the low-pressure blades in order to handle the increased volume of steam at this end. Now, continuing our examination along the length of the rotor, we come to the low-pressure end gland seal. This is at the interface between the casing and the rotor. Just on the outside of the casing is fitted the low-pressure end journal bearing. At the very end of the shaft, we find the coupling which is used to join the turbine and generator rotors. In addition, at this end of the shaft, we will often find a large gear drive which engages with the turning gear. As we'll see later, the turning gear allows us to rotate the rotor at very low speed, say 1 RPM, without having steam pass through the machine. This is used during shutdown to ensure even cooling and so prevent distortion of the rotor. More about this later. In earlier machines, the discs are shrunk onto the rotor shaft. A problem with this type of construction is that in some cases, steam may leak along the shaft and cause distortion due to differential heating as well as a loss of efficiency. To overcome this problem, in modern turbines, the discs in the shaft are forged in one piece and then machined. Yet another method of building up the rotor is by welding discs together and so eliminating the shaft. Now remember that in between each disc and associated blades, we have to fit the stationary blades. Let's see how these are held in place. The first time we examine a turbine, we might imagine that these stationary blades could be fixed to the outer casing to line up with the moving blades like this. But we do have a problem with this arrangement. What is there to stop the steam passing around the blade instead of through it? In order to prevent this, a shield known as a diaphragm is constructed, extending all the way from the inner diameter of the stationary blade down to the shaft, leaving a small clearance to allow rotation. In practice, the stationary blades are inserted into the diaphragm like this, and the diaphragm itself is fixed into the turbine casing. When diaphragms are removed during maintenance periods, they look like this. And here is a view of the bottom half of the turbine casing with the diaphragms in place. The diaphragms are sized to leave a small inside clearance to allow the shaft to rotate. Seal strips are fitted at this location to prevent steam leakage. After all, we want all steam to pass through the blading, not around it. And we'll be talking about steam seals later. When the turbine is assembled, the rotor must be very carefully lowered into place so that the discs fit perfectly between the respective diaphragms. Once the rotor is in place, the axial clearance can be adjusted and finally fixed in place at the thrust bearing. Similarly, the journal bearings must be adjusted to provide correct alignment with the generator rotor. When all adjustments are complete, the top half of the casing, which is a mirror image of the bottom part, is very carefully lowered into place and finally bolted down. The exterior of the turbine casing must be very well insulated to prevent heat loss. With temperatures at the high pressure end in the region of 1,000 degrees Fahrenheit, we could suffer a considerable loss of efficiency as well as an uncomfortable turbine room if the insulation was inadequate. Now, in this segment, we've looked at general features of turbine construction. Using this information as a guide, make sure that you check and the essential support systems. Now it's time for us to turn our attention to steam turbine operation and control. And we'll begin by looking at the means of adjusting the turbine's speed or turbine output. The principle of turbine control is very simple. If we need to increase the power output of the turbine, we have to pass more steam through the turbine. Conversely, in order to decrease power output, it is necessary to decrease the amount of steam admitted to the turbine. Turbine steam flow is controlled by adjusting the turbine admission valves, or control valves as they are often called. In the most simple arrangement shown here, we have one control valve, which, depending on its setting, allows more or less steam to flow into the turbine from the steam chest. When the turbine stop valve is open, the steam chest is charged with steam directly from the boiler. In most turbines, multiple control valves are used as shown here. In this particular arrangement, the steam chest is located above the high pressure end of the turbine shell. We can see here 8 valves, and these are opened in sequence according to the position of the crossarm, which is itself adjusted by the hydraulic control system. These control valves are set in such a manner that only one valve at a time is actually throttling steam, while the others are either fully open or closed, depending on the actual load. The result is that the throttling losses are smaller than in the case where only one large control valve is used. In large machines, say greater than 100 megawatts, it is more common to have 2 steam chests, one above and one below the shell, or located one on either side of the turbine. In this case, multiple control valves are located in each steam chest, with steam lines connecting to the turbine shell at the high pressure end. In most arrangements of this type, a stop valve is fitted at the entrance to each steam chest. During normal operation, the stop valve remains in the wide open position, while the control valves are modulated to adjust steam flow. The actual opening of the control valves is determined by the position of the operating lever, and this in turn is adjusted by the power cylinder of the hydraulic control gear. This schematic shows us a simplified version of a hydraulic control scheme. In this particular arrangement, a mechanical governor is used to sense turbine speed. Other types of governors are also used, as we'll see in a moment. In this configuration, a change of turbine speed causes the centrifugal weights to move. For example, a decrease in speed causes the centrifugal weights to move inwards and lower the pilot valve. This, in turn, allows more high-pressure oil to enter the power cylinder and raise the piston against the compression spring. This movement of the power piston opens the steam control valve and allows more steam to enter the turbine, which causes its speed to increase. Also note, as the power piston rises, the reset lever lifts the pilot valve back into the neutral position again. On large turbines with multiple control valves